This is section 3.2, part A, least squares regression. Linear relationship between two quantitative variables are pretty common and easy to understand. Correlation measures the direction and strength of these relationships. When a scatter plot shows a linear relationship, we like to summarize the overall pattern by drawing a line on the scatter plot. A regression line summarizes the relationship between two variables, but only in a specific setting, when one of the variables helps explain or predict the other. There is a caution. Regression, unlike correlation, requires that we have an explanatory variable and a response variable. So a regression line is a line that describes how a response variable y changes as an explanatory variable x also changes. We often use a regression line to predict values of y for a given value of x. Some people don't gain weight even when they overeat. Perhaps fidgeting and other non-exercise activities, or NEAs, explain why some people may spontaneously increase non-exercise activities when they feed more. Researchers deliberately overfed 16 healthy young adults for 8 weeks. They measured fat gain in kilograms as the response variable and change in energy use in calories from activities other than deliberate exercise, such as fidgeting, daily living, and anything like that, as the explanatory variable. Here are the data. So do people with larger increases in non-exercise activities tend to gain less fat? So if we look at the data and you put this data into a scatter plot, the scatter plot shows a moderately strong negative linear association between the non-exercise activity change and the fat gain with no outliers. If you calculate the R value, you're going to get an R value of negative 0.7786. The line on the plot is a regression line for predicting fat gain from your change in the non-exercise activities. So a regression line is a model for the data, much like the density curve we used in Chapter 2. The equation of the regression line give a compact mathematical description of what this model tells us about the relationship between the response variable y and the explanatory variable x. Suppose that y is the response variable, which is plotted on the vertical axis, and the x is the explanatory variable, which is plotted on the horizontal axis. A regression line relating y to x has the equation of the form of y hat is equal to a plus bx, where y hat is the predicted value of our response variable for a given value of the explanatory variable x. B is the slope of the line, or the amount by which y is predicted to change when x increases by 1 unit. And A is the y-intercept, or the predicted value of y when x equals 0. Although you are probably more used to the form of y equals mx plus b, for the equation of a line in algebra, statisticians have adapted a different form of the equation for the regression line. So sometimes you will see it in the form of y hat is equal to b sub 0 plus b sub 1 times x. But we're going to use y hat is equal to a plus bx for 2 reasons. 1, it's simpler, and 2, this is the form our calculators use. So don't get so caught up in what the symbols are. Just remember whatever variable is with your x describes the slope, and the one that does not have the variable is your y-intercept. So we have a regression line for the fat gain versus the NEA change, and our equation is the fat gain is equal to 3.505 minus 0.00344 times the non-exercise activity change. We need to identify the slope and the y-intercept for the regression line and interpret each value in context. Now remember, the slope is the one that is multiplied by your variable. So we do know that our slope is going to be negative 0.00344. And this tells us the amount of fat that is going to be gained that we can predict for every 1 unit of change in our NEA. So we predict that the fat gain will go down by 0.00344 kilograms for each 1 calorie burned more in the NEA change. The y-intercept is the one that is by itself. So our y-intercept, or A value in this case, will be 3.505 kilograms. And this is what our fat estimate of gaining would be if there is no change in the NEA. The slope of a regression line is an important numerical description of the relationship between the two variables. Although we need the value of the y-intercept to draw the line, in statistical meaningful only when the explanatory variable can actually take a value that is close to 0. Not all settings is going to actually let this happen. So you cannot say how important a relationship is by looking at the size of the slope of the regression line. So we have this equation for our NEA and fat gain data. We need to predict the fat gain for a person whose NEA change increased by 400 calories. So to do this, we're just going to do 3.505 minus 0.00344 times the NEA change in calories. And if you put that into your calculator, you're going to see your predicted fat gain, and we know it's the predicted fat gain because it has the hat over it, would be 2.13 kilograms. The accuracy of prediction from a regression line depends on how much the data scatter about the line. In the case of the fat gains for similar changes in NEA show a spread of 1 or 2 kilograms. The regression line summarizes the pattern, but gives only rough, accurate predictions. Your predictions can only be as precise as your regression line is to your data. So the better your R value is, which means the closer it is to 1 or negative 1, the better your predictions will be with your equation. For values that are outside the set of X values for our data, we cannot say whether these values can occur. For these values, we have to do an extrapolation of the relationship beyond what the data shows. So if our data that we're collecting is talking about the weight of mice from birth until they're 10 weeks old, if you try to make a prediction for when the mouse is 2 years old, that would be an extrapolation. Extrapolation is the use of a regression line for predictions far outside the interval of values of the explanatory variable x used to obtain the line. Such predictions are often not accurate. Often using the regression line to make a prediction for x is equal to 0 is also an extrapolation. That's why the y-intercept isn't always statistically meaningful. So you need to be cautious. Few relationships are linear for all values of the explanatory variables. Don't make predictions using the values of x that are much larger or much smaller than what actually appears in your data set. So let's check our understanding. Some data were collected on the weights of male white laboratory rats for the first 25 weeks after their birth. A scatter plot of the weight in grams and time since birth in weeks shows a fairly strong positive linear relationship. The linear regression equation is that the predicted weight is equal to 100 plus 40 times the amount of time in weeks. What is the slope of the regression line? And explain what that means in context. Now remember, your slope is the one that's attached to your variable, and this time our variable is time. So our slope is going to be 40. This means that we predict that a rat will gain 40 grams in each week of its life in the first 10 weeks, or first 25 weeks. What's the y-intercept, and explain its meaning? The y-intercept would be 100, and this suggests that we expect a rat to weigh at birth 100 grams. Predict the rat's weight after 16 weeks, and we need to show your work. So to find the predicted weight, remember you're just going to plug this into your equation. So 100 plus 40 times 16, and this would give you 740 grams when the rat is 16 weeks old. Should you use this line to predict the rat's weight at age 2? Use the equation to make the prediction and think about the responsibleness of this result. It is good to note that 454 grams is equal to 1 pound. So, should you use this line to predict at 2 years? Our equation was collected from data from the first 25 weeks. Now, there are 52 weeks in a year, so half a year is 26 weeks. So this is for less than the first half of the rat's life. Now, we're not going to expect the rat to continue to gain weight at the same rate it does as it does the first half year of its life. So this would not be reasonable for us to use this equation to predict the rat's weight after 2 years. But if we did use it, we would plug this into our equation and we would get 4,260 grams, which is approximately 9.16 pounds. It is not reasonable that the rat is going to weigh 9.16 pounds at the age of 2 years.